Hi guys, so today we're going to continue looking at exponential functions. Today we're going to look at writing them both from word problems and application purposes, and also just rewriting these into different forms in order to be able to tell if our graphs are growing or decaying. So the first thing we do is just kind of practice our exponent properties. All right, so we're going to rewrite the function 2 to the 2x into a form where the exponent is just x. Well, we can do that using our exponent rules. So if you have multiplication in the exponent, that means that you have a power raised to a power. So 2 to the 2 to the x is 2 to the 2x. Well, another way that I could write that is y equals 4 to the x. So what that means is that those two functions are the same thing. All right, this also helps you hopefully explain why we said a function like this shows decay, but also a function like this shows decay. Because using exponent properties, 2 to the negative x is the same thing as 2 to the negative 1 to the x. 2 to the negative 1 is 1/2. So those exponent properties allow us to kind of rewrite these into different forms depending on what we're trying to see and trying to do. So we're going to use that same idea to try and rewrite these functions into a form that looks like this. The reason that we're using those forms is because those forms show our growth and decay rate. So the first equation obviously shows growth. The second one obviously shows decay. So we're going to rewrite this as a times 2 to the 1/3 to the x. Because using exponent properties, 1/3 times x would be x over 3. So now I can go ahead and rewrite that. I can actually evaluate what 2 to the 1/3 is on a calculator. So when I do 2 to the 1/3, I end up with 1.26. So then I can rewrite this again into that form where it's 1 plus 0.26 to the x. So this obviously shows growth because the base was greater than 1. And now by separating it into 1 plus 0.26, that makes it really clear that this graph is showing a 26% growth rate. All right, let's try and rewrite b. Okay, so I'd rewrite this as a times 0.5 to the 0.5 to the 1/12 to the x. So I'll actually plug into a calculator 0.5 to the 1/12. So 0.5 to the 1/12 gives me 0.944, which then tells me that it's looking at decay because that's less than 1. Well, now I can rewrite that as 1 minus 0.056 to the x. So we know this is showing decay, and now we can tell specifically it's showing a 5.6% decay. All right, we can follow this same process if we have a base of e. So let's rewrite it. All right, so e to the negative 0.5, again, I can evaluate that on the calculator. Plug it in, and if you don't know where the e button is, that is maybe a little new for you guys. So e, if you guys see on your calculator, if you're using the Casios, where it says ln, well, right above that it says e to the x. So if you do shift and that ln button, that's how we'll get e. So we're going to do shift e, and we're raising that to the, can't see my original problem, to the negative 0.5. So that gives me that rate. So I can rewrite this now as 0.607 to the x. So I can do 1 minus 0.393 to the x. So again, we're showing decay, and we're showing decay by a rate of 39.3%. All right, let's look at the next one. Again, 0.5 here is that a value. And when it comes to these growth and decay equations, a is the initial amount. So we'll rewrite it using our properties. We'll evaluate e to the 0.8 using a calculator. That'll give me 2.226, which I can then rewrite as 1 plus 1.226. So this is obviously showing growth, and it's a pretty heavy growth, of 122.6%. All right, so the next thing we're going to do is we're going to write equations from either graphs or from points. All right, so we're going to start with a graph. It's a pretty simple one. This graph's pretty easy because it gives us the y-intercept. Now, when you guys do your Desmos activity in class, you'll look more at transformations, shifting left and right and up and down and reflecting. For now, we're really just writing it in this form. Because again, that's the form that really helps us see these growth and decay factors pretty easily. So a times b to the x, our a value is our initial amount. Well, our initial amount here is 1. So now I just need to determine b. Well, if I raise it to the first power, I get 0.25. And if I raise it to the -1 power, I get 4. So that hopefully makes it pretty clear that your base has to be 1/4. All right, now looking at b, this one's a little bit trickier. And actually, let's go ahead and do c first, because the method we use for c, you can use for b if you want to. So what we're going to do for c, we don't know the a value, because we don't know the y-intercept. But what we have are 2 points. And if we have 2 points and 2 variables, then we can set up a system. So if I use y equals a times b to the x, I can plug in 12, and I can plug in my other points, and now I have a system. Now this system may look kind of complicated. It's really not that bad. We're going to use substitution. So let's rewrite this first equation. This would be 12 is a over b squared. So if I want to use substitution, I just need to solve for a. Well, that's pretty easy. Multiply both sides by b squared. So now I know what a is. So I'm going to take a, and the value of a, and I'm going to substitute it into this equation. And then b to the -4th, remember that's 1 over b to the 4th. All right, so this gives me 48, and this is going to be 12 over b squared. And then I'm going to go ahead and multiply both sides by b squared, or I'm going to cross multiply, whichever way you want to look at it. Divide by 48, square root both sides. Now again, typically when we square root both sides, it's plus or minus. But in this case, b is the base of this exponential function. And we talked about the base of an exponential function can't be negative, because it's not going to create an exponential graph. Because if you have a negative number that's to an even power, and then an odd power, and an even power, and an odd power, it's going to just bounce back and forth between positives and negatives. It's not going to give us a very good graph. All right, once we know what b is, we'll just take that, substitute it back into either equation. I'll go ahead and plug it into the first one. So 1/2 to the -2nd is going to be 2 to the 2nd, which is 4. So a is 3. That means my equation is 3 times 1/2 to the x. All right, now we can use that same method for this second example. But it's a little bit easier here in this example, though. I know the a value. When x is 0, okay, when x is 0, if I raise anything to the 0 power, this gives me 1. 1 times anything is just that value. So a has to be that y-intercept, which is 6. So now I just need to figure out my base. So if I want, I can use that same method. I can set up a system, but now I can plug in that a value that I know. Okay, so I could solve this, and I could say 4 is equal to 6 times b to the first. So that means that 4 over 6 is equal to b, so b is equal to 2/3. So that equation is 6 times 2/3 to the x. What you also might notice, though, if you look at the y value, let's call this point y1, or x1, y1, and we'll call this point x2, y2. If you look at the ratio of that y value over the other y value, that gives you your base. So that's another way you can look at it. And once we start doing series and sequences later on this year, we'll kind of get to talk about that a little bit more. All right, so the last thing we're going to look at and spend most of our time on are applications. So exponential growth and decay has a lot of applications to it. You may have seen some of these in Algebra 1. If not, we're going to review them. But this is your basic growth and decay model. All right, so exponential growth is modeled by this first equation. A is the initial amount. and R is your rate. And we want our rate to be as a decimal. So if it's 7%, we're using 0.07. T is time, and whatever unit you keep time in, it needs to be consistent for your problem. So let's look at this first equation. The value of a car in thousands of dollars is approximated by the model 31.92 to the T, and T is the number of years since the car was new. So first thing we need to determine, does this show growth or decay? Well, the base is less than 1, so it shows decay. It also makes sense for the problem. Your car is going to be worth less money the older it gets. All right, now let's find the annual percent increase or decrease. This is not a 92% decrease because that equation, 1 minus R, is 0.92. So that means that R is 0.08, which is 8%. Okay, so be careful with that. The number that's in your equation is not the percent. So next thing we're going to do is we're going to estimate when the value of the car will be $9,600. So 9,600 in this model is a Y value. Okay, so we're going to solve for when our Y would be 9,600. We got to be careful about a couple things though. 9,600 is not what I want to plug in for Y. Okay, look at your model. If we were going to plug in 9,600 for Y, that would mean that the car is $31 to start, which doesn't really make sense. If you read your problem, it tells you the value of the car in thousands of dollars is modeled by this equation. So this 31 actually stands for 31,000, which means that my Y value that I use really isn't going to be 9,600. I'm really going to use the Y value of 9.6 because, again, this model is in thousands of dollars. Now, later on this unit, we're going to come back to these types of problems, and we are going to solve them algebraically. But for now, the only way to solve this algebraically is using a log, and we don't know how to use logs yet. So for now, we're just going to get some practice solving these on the calculator. So what I'm going to do is I'm going to go ahead and graph my model. All right, so I have my graph in there, my equation typed in. Before I graph it, I'm going to change my window. So I need to consider what window makes sense for this problem. X is time. I don't care about negative time, so I'm going to make my X min 0. X max, so the biggest X value that I'm going to choose is the amount of time I'm going to have the car. And I can kind of estimate here, I'm just going to go with 20. We don't know how long we'll have the car, but we know it's not going to be a huge number, and I want to see enough to see a good picture of this graph. Y min, Y stands for the price of the car in thousands of dollars. So I don't need negatives because it won't reach negative. And I also need my max to be at least as big as the starting value of the car. Now it's decaying, so it doesn't need to go up much more than that. So I'm going to go ahead and make that value, we'll go ahead and just say 35. Because remember, this equation is in thousands of dollars. So now I'm going to go ahead and graph it, and there's my picture. So there's two ways to evaluate this when Y is equal to 9.6. One option is if I go to GSolve, I'm going to click F6 to see some more options, and then you'll notice your YCal and your XCal option. So YCal will give you the Y when you know the X, but that's not our problem. Whoops. XCal will give you the X when you know the Y, and that's what we're trying to do. So I'm going to plug in 9.6, and that tells me that this car will be valued at $9,600 after about 14 years. The other option, and this is an option if you have a TI that you'll probably want to use, if I go back to my equation, what I also can do is plug in my Y value into Y2. And then what I'm looking for is just the intersection of those 2 points. So I can do GSolve and intersect, and that will also give me that Y value. Now this is a good option if your problem can have more than one solution. Now in this case, we're only going to have one answer, but later on, maybe when you do your trig graphs in pre-cal, you may see multiple answers, and this might be an easier method for you so that you can see more than one. All right, so we plugged in 9.6 for Y, and that gave us an X value of about 14, so it'd be about 14 years later. All right, so let's go ahead and try a couple more. So this time we're going to write the equation. So it says the population of a city was about 1.04 million. In the next 14 years, it increased by 2.05%. So we're going to write our model. So it's Y equals initial amount, 1 plus R. So remember, we want R as a decimal. So 2.05% is 0.0205. So this is 1.0205 to the x. So if I want to estimate the city's population in 2008, I would plug in 8 for x. If I want to know the year that the city's population is 1.3 million, my model is in terms of millions, so I can use 1.3. And again, I can do either Y2 and intersect, or I can do GSolve, and then I can do XCal, and I can plug in 1.3. So whichever method I decide to use, on the first one, I should end up with 1.22 million. On the last one, I'm going to end up with about 11 years after. And 11 years after would be the year 2011. All right, so one more using this type model. We'll get into some more half-life type questions when we get to logs. But for now, this is just showing kind of that decay idea for an element. So it wants to know the percent that decays each day based off of this model. There's actually two different ways that you can solve this equation. So one of them is we can use what we did at the very beginning of the notes. I can rewrite this model into the form of a 1 minus r to the x. So using exponent properties, I can rewrite this as 0.5 to the 1 over 13 to the t. I can plug in 0.5 to the 1 over 13 to a calculator, which is going to give me 0.948 to the t, which I could then rewrite as 1 minus 0.052. That makes it pretty clear that my decay rate then is 5.2%. The other way you could work this out is actually see how much is left after 1 day. So let's just say I start with 1 gram, and I want to see how much of that 1 gram is left after 1 day. It's really the same problem, we're just setting it up a little differently. I would still do 5 to the 1 over 13, which is going to give me 0.948. So that means that there'd be 0.948 grams left, which means that 0.052 grams decayed. And 0.052 of 1 would be a 5.2% decaying rate. So either of those options will work. All right, so the last two applications we're going to look at are about compound interest. So you might have saw this in middle school at some point, but the way compound interest works, the more often your interest is compounded, the more money you're going to have. Now, it's not a huge difference, but it does make some difference. So we're just going to look and see how compound interest works. So we're going to take $100 and 10% interest. Well, if it's compounded yearly, which is just simple interest, after year 1, I would start with $100. I would get my 10% interest, and that would give me $110 at the end of the year. Well, year 2, I'm still going to get 10% interest, but I'm starting the year now with $110. So that 10% interest is now $11. Then I would go to year 3. I would start with $121. I would get my 10% interest, which is now $12.10, which puts me at $133.10. So you can see you keep getting a little bit more interested each year just based on the interest that you've earned the previous year. Now, if that money was compounded more frequently, let's say it was compounded quarterly. Well, let's look at the first quarter. What you would do is you'd start with $100. You're still getting 10% interest, so I'm still getting $10. But at the end of the first quarter, I've only gotten a fourth of that interest, which is $2.50. So at the end of the first quarter, I have $102.50. Well, now when I do my second quarter interest, I'm still going to do a quarter of the 10%, but it's a quarter of the 10% of $102.50. So that 10%, sorry about that, that quarter of that 10% is $10.25. So that's my 10%, and I get a quarter of it. So that's going to give me $105.06. Then I go to quarter 3. I start quarter 3 with $105.06. 10% of that is $10.51. I'm only getting a quarter of the interest because it's a quarter, and that's going to give me $107.69. Then I go into the last quarter. Again, I'm starting with that 107.69. I'm going to get a quarter of that 10%. So 10% is 10.77. Only getting a fourth of it though. And that's going to give me $110.38 at the end of year one. So if you notice, it's compounded more frequently, you're getting that extra 38 cents. And I know it doesn't seem like a lot, but if you have a pretty high interest rate and a lot of money, it really can make a pretty good difference over this certain period of time. So here is your compound interest formula. Again, you may have seen this in either Algebra 1 or maybe in middle school. A is the amount after however much time. P is the principal, which is your starting amount. R is your annual interest rate. It's always written as an annual interest rate. And we want that as a decimal. T is my time. It has to be in years because it's an annual interest rate. N is the number of times your money is compounded in 1 year. So all this stuff is in relation to years. So if N is the number of times it's compounded in a year, if let's say it's compounded quarterly, N is 4. Compounded weekly, N is 52. Compounded yearly, N is 12, just depending on what that is. So we've got two equations to set up here. So I've got two accounts with $10,000. One of them pays 1.65% annual interest, and it's compounded daily. So let's start with that one. So $10,000, then 1 plus 0.0165. Again, we write it as a decimal. Compounded daily, that's 365. And then 365, we want to know how much is there after 5 years. So I'm going to multiply that by 5. All right, we can go ahead and just plug that in a calculator, figure that out, and I end up with $10,859.97. All right, let's look at account number 2. I'm still starting with $10,000. My interest rate's a little bit different though, 0.0168. This one's compounded quarterly, so that's 4 times a year. So then 4 times 5 is in my exponent. I can take that, plug it in a calculator, and I end up with $10,874.38. So account number 2, even though it was compounded less frequently, that higher interest rate made a bigger difference for us and is going to give us more money. All right, now the last one you probably have not seen before because E is something new that we just looked at this year. So continuously compounded interest. This is if, let's say your interest isn't just compounded daily. It's not compounded hourly. It's not compounded by the minute or by the second. It's compounded as infinitely many times as it can be compounded. That is going to use the value of E because that's the only way basically you can show as it's compounded as much as it possibly can. Now that might seem like it's going to be some crazy huge amount, but if you think about it, if you keep taking those fractions of fractions of fractions of fractions of interest, well, once it's less than 1/100th of a difference, it's not going to make a change on your account because we don't take care about millionths of a penny, okay? So it's still going to be pretty comparable to these other ones, but it is the fastest rate at which interest can compound. So this is the form that we're going to use. Looks like the word PERT, makes it pretty easy to remember. E is the Euler's number E that we talked about last class. So let's say we have $5,000 to invest. It earns 1.75% annual interest. It's compounded continuously. So if you see that word continuously, that is when you use this PERT formula. If you see that it's compounded any other period of time, you use the other formula. So how much money will we have in 10 years? Let's start with that question. Well, A equals 5,000 E to the 0.0175 times T, which is 10. Plug that straight into a calculator, and you'll end up with $5,956.23. All right, option 2, when will you have $7,000? So let's write our equation in terms of x for time, because we don't know the time. So this will be 5,000 e to the 0.0175x. We can graph this. We can xcal, and we want to xcal for 7,000. Or again, we can y2 and intersect, but xcal 7,000, and then I end up with about 19.23 years. Again, we're going to come back to these later on in this unit when we do logs and actually solve these algebraically. But for now, it's good to just get that practice in how to solve these on the calculator. All right, so that is it for writing equations. Last thing with exponential functions we're going to look at is regression next class, also on the calculator. And then we'll move on to logs.